Hi, in this module we are going to learn about timing sequential circuits. So we talked about how we analyze combinational circuits and delay for combinational circuits, and in this class we will look at the timing constraints required for sequential circuits. So we looked at two different components for sequential elements. For flip flops we looked at the notion of what is called setup time, and we looked at the notion of what is called hold time. So just to jog your memory, so setup time and hold time together form a window, and this window is for a flip flop is around the clock pulse that is triggering it. So if it is a positive edge triggered flip flop, around the positive edge trigger you place a window. So for some time before the clock edge arrives, and once the clock edge arrives for some time, for this time window you cannot change your data. The data has to settle in before the clock pulse comes, at least TSU time units before that, and it has to be held at the same value at least for TH time units after it arrives. So we saw these two things, but as we saw in the previous week, we saw that the circuit, a sequential circuit, is not just the sequential elements, it also has combinational logic around it. So what we are going to do is we are going to look at how we analyze for a sequential circuit, not just a element. So let us look at the basic sequential circuit. This is the same picture that I showed earlier. We have state registers, and there is some input forming logic and output forming logic, or the next state and output logic. The inputs come into the input forming logic, the inputs also go to the output forming logic, and so on. Now what we want is, we want timing relationships. So if I look at this whole thing as a black box, as a chip, there are inputs that I am providing. This may also include the clock, and there are outputs that are coming out. So for instance, this could be a chip which I have put on a motherboard, and the clock input and the data inputs are coming from the external world, and the output that is coming out of the chip is going into the external world. So a signal that is placed on the chip's input will take some finite amount of time to go inside. It has to go to the input logic which is inside your chip. It has to go to the state register which is again inside your chip. Finally the output that is coming out from your chip has to come out and travel through the bus that is in the printed circuit board or the motherboard, and then go to another device. So there are quite a few things that happen in a system. So if we imagine this as a chip, then there are inputs and outputs that are external to it. We want to see at what rate you can supply the input. So you do not want inputs that are given too fast, the circuit may not be able to process it at that rate. You also do not want the inputs to be too slow, because if I can process it at a higher rate, why not? So we want to be able to see at what rate I can give the input and at what rate I can sustain the output. So this is called sequential circuit timing analysis, and we will look at timing problems that come because of various constraints. So let us look at the basic parameters. In terms of the whole chip, we first talk about what is called capital T subscript SU, or the global setup time, and we will also look at what is called the global hold time. So we are going to assume that there is a clock pulse that is fed from the external world, and with respect to that clock there is some data that is coming from the external world. So we will first argue that with respect to that clock pulse we need to satisfy two timing parameters, namely global setup time and global hold time. We also want to look at what is the largest frequency at which a chip can run. So if I design a circuit, then I want to see at what frequency it can run. So high speed circuits are circuits that can run faster. So sometimes you want circuits that can run very fast, and you want to be able to clock it at as much a high frequency as possible. So if I am making a processor, if I can change the design a little bit, and if I can run it at 2 gigahertz instead of, let us say, 1.5 gigahertz, then that is a nice thing to do. So we will see how to do all of that. There are various parameters or definitions that you need to know, but it is fairly straightforward. So let us look at the subscript here in each of these parameters. So wherever you see a I, that relates to inputs which are given to the chip. Wherever you see O, these are outputs from the chip. So imagine a black box around this. This is all inside a chip, but there is something coming from the external world, there is something going to the external world. So this I relates to input, O relates to output, and F relates to flip flop. So, let us see these 4 parameters. I to O means the delay that it takes to go from the input, a change in input, it goes through the input forming logic and then appears as input to the flip flop, that is called I to O is going through the inputs to the output logic to the output. I to F delay is from the inputs going through the input forming logic, how long does it take to appear as input to the state register, that is called I to F. So, the moment there is a change in the flip flops output, how long does it take to go to the output, that is called F to O delay. So, the delay should account for output forming logic's delay, and then there is flip flop to flip flop delay. If there is a change in output in the state register, how long does it take to go back through the input forming logic to come back and appear as input to the state register. So, that is called flop to flop delay. So, flop to flop delay, so all these if you notice are all combinational delays, IO, IF, FO and FF are combinational delays. Then there is C to Q delay. This C to Q delay is the clock to Q delay of the flip flop that you are using. There is SU and H which are also delays of the element. So, the moment you pick the flip flops that you are going to use in your circuit, T C to Q, T SU and T H are the clock to Q setup and hold time of the flip flops. Finally, there could also be something called TC or the clock delay. This is the time required to reach all the flip flops. So, there is a clock that is given as an external input to the chip, and this goes through the bus onto the chip, and at the chip it still has to travel within the chip to go and reach various flip flops, and we will call that the TC or the clock delay. So, for now just remember that we are looking at parameters, these 4 parameters are combinational delays and these 3 parameters are flip flop basic unit delays, and this is something which is respect to the external world. So, let us first look at the global setup and hold time. So, the global setup time is as seen from the outside of the chip, when the clock pulse comes in, how long should the data be ready before the clock pulse comes in, and how long should the data be ready, should be kept stable after the clock pulse comes in. This is called the global setup and hold time. So, let us see a signal called CLK. I am going to assume that the whole circuit is synchronous with respect to positive edge trigger of the flops. So, let us assume that there is an external source called CLK, and internally it takes TC time units to appear at a flip flop. So, this could be because of the wire that connects from the input pin to the actual flip flops clock input. So, this TC could be 0, but let us assume that TC is some positive quantity right now. So, we will call that signal as CK. So, CLK is from the external world, CK is as seen at the flip flops. Now, you are bringing data from the external world, we will call that X. When this appears in the input of the flip flop, we will call that D. Now, any change in input in the external world is going to go through the input forming logic and appear as inputs at the flip flop, that will take TIF time. So, that is the input to flop delay, right. A change in input at the external world will go through the input forming logic and it will appear as D inputs, that is going to take IF time units. So, some change in input here is taking IF time units, then there is another change in input from here. So, if you notice there is a change in input here, that is going to take some time unit TIF and so on. So, TIF is the time period between X and D. So, we are assuming that there is somebody watching all the events in the chip and we are drawing the waveforms with respect to that observer. So, there is an observer who is seeing all the events with respect to the chip. So, from the external world the data changes at this time period, but it takes TIF time units to appear as the flip flop input and so on. So, that is TIF. Then our TSU and TH are actually specified with respect to the flip flop. Remember this small case t subscript SU and small case t subscript h are actually with respect to the flip flop. So, let us go and look at that with respect to CK, not CLK, with respect to CK, because that is your flip flop device. So, with respect to the flip flop, there is some period of time before which the data has to be stable, and some period of time after the clock pulse arrives it should be kept stable. So, TSU plus TH are a window around CK, not CLK. Now, I want to know the relationship between the external in the external world. So, this is the external clock signal, and how long should I keep the data stable with respect to the external clock signal, that is the global setup time, and how long should I keep it stable after the external clock trigger with respect to the input data, that is called the hold time. So, what we are looking for is the mathematical relationship between capital T SU and the parameters here and capital T H and the parameters here. Can we derive TSU and TH in terms of various circuit parameters? This is what we are going to do in the class today. So, let us see this. Let us look at TSU. So, we are trying to measure the time between here, because this is where the external input is allowed to change. By this time it should have settled down, you do not want it anywhere beyond that to the left side. So, that is your TSU, and we are trying to measure the time period between this vertical line here and this vertical line here. What is the allowed setup time? So, if you go and look at these parameters here, I am going to write an expression first. So, TSU, the capital TSU is TSU max plus TIF max minus TC min. So, let us look at this. From this line here I want to measure up to here. So, TIF plus TSU minus TC brings me to this edge, right. So, that is TIF plus TSU, that takes me to the clock pulse here, but if I subtract TC it takes me to CLK. So, TSU is TSU of the flip flop plus TIF which is the input to flop delay minus TC. Let us look at these maxes and mins. So, if there are multiple paths from input to the flip flop, the largest of the flip flops, the largest of the input to flop delay should be accounted for. If I have different kinds of flip flops with different setup times, I should account for the largest setup time, and if there are different flip flops, some flip flops may be closer to the external world and some flip flops may be far away from the external clock trigger. So, the smallest of that should be accounted for. If I account for all of these, then TIF plus TSU minus TC gives me the global setup time. Let us look at the global hold time. The global hold time, it starts from when the external CLK trigger comes, and for some period of time you have to keep this green data stable. You cannot switch the green data, that is with the external world. X cannot change for some time period. We want to see how long it can be. So, if you look at the picture here, TH is TC plus TH of the flip flop minus TIF. So, let us put it down. So, capital TH is capital TC, so this TC plus TH of the flip flop minus TIF. So, this is just written in a rearranged manner. So, it is TIH minus TIF plus TC. So, it is the same expression written in a different form. Now, let us go and look at the max and mins here. So, I want to wait for the largest hold time among any of the flip flops and the largest clock to external CLK to CK delay for all the flip flops. So, that gives me TH max plus TC max, and the reason why you have to wait for the smallest one is if there is a change in the input through the shortest path, it can go to the D input, and this may upset your flip flop, it may violate the hold time. So, with respect to TH, the hold time constraint can be violated because of the shortest path, which will have the delay of TIF minimum, and with respect to the external world, the longest path or TIF max can actually violate the setup time. So, TSU and TH, you can see the mathematical expressions. Even if you do not have the max and mins, just get the expression right. It is TSU plus TIF minus TC, and TH is TH plus TC minus TIF. These are the global setup and hold times. These are with respect to the external world. And if you want, so there are various parameters I talked about, right. We are worried about the global setup time, the global hold time, and what is the frequency at which I can run the circuit. So the frequency at which I can run the circuit, I should look at what's happening within the chip. Let's look at the chip inside. So there is the CLK here. Let's assume that there is no delay between CLK and CK. Let's for now assume that TC is 0. Right. CLK appears as CKI and CKJ. Let's assume that there is no delay between the CLK signal and CK signal as of now. Then let's assume that there are two flip flops, QI and QJ. QI goes through the combinational logic and it may influence DJ, and QJ similarly may go through the combinational logic and influence DI. In fact, QI could influence DI and QJ could influence DJ. So there are 4 flop to flop paths here, QJ to DJ, QJ to DI, QI to DI and QI to DJ. There are 4 flop to flop paths. If I want to find out for an edge triggered circuit the smallest clock period, the smallest clock period is one in which it accommodates for all the delay that can happen in the circuit. So what are the delays that can happen when you go from one flop to another flop? So as soon as the clock pulse comes in, the data could change. So that is TC to Q delay. So let us say DI is stable for a while, let us assume that. So you bring the clock pulse CK, as soon as you bring the clock pulse this Q can change. So that is the clock to Q delay. Then you go through the flip flops, that is the FF delay, and then you have to still account for the setup time of the flip flops here, right. So if I go, let us say I am looking at the constraint from I to, so from QI to DJ if I want to look at it. So this clock to Q delay of this flip flop plus the path through this combinational logic plus the setup time of this flip flop. If I add all of that together, then so any change in here will take at least so much time to appear here, which means my clock width should be greater than that, so that any, if I place the current state here to get to the next state, I need to have at least so much time accounted for. So I have to delay the clock pulse by at least so much time unit, and that is why you have the greater than or equal to symbol here. So T of the clock or the width of the clock should be greater than TCQ max plus TFF max plus TSU max. So in fact T clock should be greater than CQI plus T flip flop to flip flop. So essentially I to QI to DJ delay plus TSU of this QJ flip flop. There will be 4 such constraints, QI to DJ, DI to QJ, then QI to DI itself and QJ to DJ itself. There are 4 such things. Since TC clock should be greater than each one of these 4 summations, then you can as well write it as max. So TCQ max plus TFF max plus TSU max. In each of the terms you pick the largest quantity. This is the most conservative clock that you can have. T clock is greater than the worst case clock to Q delay plus worst case flop to flop delay plus worst case setup time. You add all of that, your width of the clock must be greater than that, which means the clock frequency is upper bounded by 1 by T clock. So this is with respect to maximum clock frequency. Here we assume that CLK appears immediately as CKI and CKJ. So the derivation you can see here. So CKI, TCQ, TFF and TSU. So CKI is here, this is the, so as soon as the clock comes QI could change the value after TCQ units. After some flop to flop delay DJ changes, but before the next clock pulse comes. So this is the launching clock period and this is the landing clock. So as soon as this closes, you C to Q plus flip flop, so it will start appearing at DJ now. However, you still have to satisfy the setup constraints of the landing flip flop. So you go and push it till that. So TCQ plus TFF plus TSU, that should be, that is how wide the clock pulse must be. So I hope this is clear. So what could happen is if you violate that condition, T clock is greater than the summation of these, then we have what is called a setup time violation. So if T clock, so the first thing is T clock is bounded by TFF max. So your clock should be at least greater than, however fancy your flip flop is, the flip flop only controls TCQ and TSU. So instead of a D flip flop, if I use a T flip flop, or I get a better design for a D flip flop and so on, it can only change CTQ and SU max. This FF max is a function of the combinational logic that you used. So T clock is has a lower bound of TFF max. It should be at least TFF max first of all. Then if the clock period is equal to TFF max plus TCQ max, let us assume that T clock is not greater than or equal to this sum, it is only just greater than CQ plus TFF. Then what can happen is the flip flop is said to violate the setup time. So if there is a setup time violation, then one way to look at it is, so you want this summation to be, this T clock to be greater than this summation, however you are not able to satisfy it, then I can bring down any of these quantities and make T clock greater than or equal to this. So this is something that is under your control, but sometimes you have a target, I want to design a 2 gigahertz chip, right, in which case T clock will be 0.5 nanoseconds. So if I want a chip at a certain target, then I have to go and redesign either the circuit or redesign the flip flop so that the setup times are not violated. So there is one which is the analysis, given a circuit you can tell me what is the largest clock width that you need. Sometimes you are given synthesis, you are asked for a specific T clock, you have to go and design the circuit in such a way that you never violate this condition. So if you violate the setup time, you have to go back and change either the flip flops you are using or come up with better circuit so that the FF max goes down. Then there is this notion of what is called clock skew. In the earlier case we assume that CLK, which comes from the external world, appears at CKI and CKJ magically immediately. But remember, we are talking about electrical signals. The electrical signals also take some time to go from the outside of the chip to the clock pins of the flip flop. We call that T skew. So skew in English means change, right? So if there is a skew, there is some change. So clock skew is the difference in the time between the triggering edges seen at the different flip flops. So let us see this circuit here. So you have CLK and you have CKI and CKJ. What could happen is, so imagine I am speaking, right? So or I am shooting a LED light, right? So if I shoot from here, the LED, so if somebody at a closer distance will actually see the light earlier than somebody at a larger distance. So forget the fact that the speed of light is very high compared to human perception, but you can imagine that the light arrives or even sound waves arrive at somebody who is closer earlier than somebody who is later. So the same thing happens here. If CLK pin from the external chip is closer to the flip flop I, then CLK will be seen at I earlier than CKJ. So the same clock pulse between CKI and CKJ, you will see, you may see that there is a difference. That is what we call a skew. So let us see the waveform first, we will come to the equation next. So you have CKI, which is the clock as seen by the flip flop I, and CKJ could have what is called a positive skew or a negative skew with respect to J. So CKI is here, CKJ may be some T skew time units away, because the flip flop is away from the CLK pin. It could be that CKJ is actually seeing the clock later. Now if I want to look at the relationship between CKI and CKJ, let us look at the timing relationship. So we are looking at the delay from flip flop QJ to flip flop I. So we are looking at this path starting from QJ, what happens if you have to go to I. So the moment CKJ comes through, then you have a clock to Q delay of the QJ flip flop, you have to account for that. Then you take TFF time units through this combinational logic, then DI gets ready, and you have to get the DI ready for at least setup time unit before the CKI comes. So this is the launch edge of the data and this is the landing edge, right. So, your clock pulse should take care of the fact that this T skew plus TCQ plus TFF plus TSU, right. So, the launching flip flop is CKJ, the landing flip flop is I, and the launching flip flop is actually seeing its clock late, which means it has lesser time to get the whole data ready, so that the landing one can actually see it at the right time without any violation. So, that is what you have here. TCLK is greater than or equal to TQ max plus CQ max plus FF max plus SU max, all of them are considering the largest values. So, if CKI comes slightly to the left, which means CKJ is not too much delayed compared to CKI, then you have a little more breathing space. In fact, if it comes at the same time as CKI, then TSQ is 0, you get a little more breathing space. If it comes before CKI, then that is actually good, because then you have a lot more space. So, if the direction of the difference in clock and if the direction in which the data is going, so CKI is earlier than CKJ, but CKJ is providing something to DJ, right. So, CKJ is providing something to DI. So, the data is going in the opposite direction of the clock, so that is a tighter constraint. If it goes in the same direction, then it becomes slightly easier. So, this is called skew. Let us do a small example. So, we have a circuit, let us not worry about what the circuit does. There are two external inputs A and B, and there is an external input called clock, and we are looking at what is the time at which the, we want to do the timing analysis of this circuit. We want to look at various timing parameters like TSU, TH, what is the frequency at which it can run, and so on. So, the same circuit is given here. Let us do analysis of this. Any change in CLK is going to take some time period to appear as CK, and that happens to be two NAND gates in the path. The NAND gates used, we say that TP max is 10 nanoseconds and TP minimum is 3 nanoseconds, which means the largest delay is 10 nanoseconds and the smallest propagation delay is 3 nanoseconds. So, TC minimum is 2 times TP minimum of the NAND gate, so 2 times 3 is 6 nanoseconds, and TC max is 2 times TP max of the NAND gate, that is 2 times 10, which is 20 nanoseconds. So, these two parameters are the easiest to derive. Now, let us go and look at IF max, IF min, FF max and FF min. So, if you look at IF max is from the input, what is the largest time it takes to go to the D flip flop. So, clearly there is a path from A through here to go here, and there is a path from B through 3 gates to go to D. So, if I assume that the smallest delay here and the smallest delay here are added up, right, then that is the smallest IF, right. So, IF minimum is 1 NAND gate here and 1 NAND gate. So, this 2 and OR with 2 NOT inputs is equivalent to a NAND gate. So, 1 NAND gate delay plus 1 NAND gate delay is the smallest path. So, that is 3 times, so 2 times TP min of NAND. So, you look at the smallest propagation delay of NAND, that is 3. So, 2 times 3 is 6. The longest time it will take is, if there is a change in B, it has to go through 3 NAND gates first of all, and the NAND gates we could be exercising the worst case path, the largest propagation delay of the NAND gates. So, you take the largest of the delay, that is 3 times 10, which is 30 nanoseconds. So, TIF max is 30 and TIF minimum is 6. Let us look at flop to flop delay. A change in Q bar can go through 2 NAND gates and appear as D, right, or a change in Q could go through 2 NAND gates and appear at D. So, if either one changes, it will take at least 2 NAND gates to go there. So, FF minimum, you take the minimums, so that is 6 nanoseconds, and FF maximum, you take the maximum of the NAND gate, that is 20 nanoseconds. So, this takes care of all the paths, I to F to F, both minimum and maximum. So, if you look at the global setup time is TSU max plus TIF max minus TC min, this is just summation, 2 plus 30 minus 6 is 26 nanoseconds. The whole time, the global whole time is TH max plus minus TIF min plus Tc max, these are all just equations that I derived earlier, that is 29 nanoseconds. TCLK is TCQ max plus TFF max plus TSU max plus, actually there is a TSQ max, but we are looking at the clock pulse, the launching edge is on flip flop Q, the landing edge is also flip flop Q, there is no skew there, so skew is 0, so the skew is 0 here, you add all of that up, that is 42 nanoseconds. So what this essentially says is your clock frequency cannot be more than 23.8 megahertz, and when the clock pulse comes in the external world, at least 26 nanoseconds before and at least 29 nanoseconds after, so roughly for about 55 nanoseconds you have to keep the data stable at A and B. A and B should be stable for 55 nanoseconds, 26 nanoseconds before the CLK comes in and 29 nanoseconds after the CLK comes in, you have to keep it ready, which means for 55 nanoseconds you have to keep your external inputs stable. So if there is some other circuit that is going to drive A and B, you should ensure that that is keeping the data stable for at least 55 nanoseconds and 26 before and 29 after. So this is for sequential circuit with the actual clock delay also. So you can also do the same thing with latches. So I am going to leave you with the equations here, and I want you to go and think about why these equations are correct. So we are looking at width of the clock pulse. The argument is that the clock pulse should be at least so much wide and at most so much wide, right. So this one says TW is at most so much, it has to be, it cannot be greater than TFF min plus TDQ min. This one says it should be at least so much, TDQ max plus TFF max plus TSU max. This is about width of the clock. So I would like you to go and argue that this is actually true. So go and think about why this should be true. What I want to show is the clocking frequency with latches. So let us look at a circuit here. Here these are not flip flops, these are latches, and we have a circuit like before except that these two are latches. So I want to now derive the relationship for clock frequency of latches. So we have various signals here, we have Cky, Ckj, Dj to Qj, and Di. So we have several data inputs, so Dj, Qj, Di and so on. I want to look at the relationships between various parameters. So if I want to look at what is the width of the clock, that is the rate at which you can give the inputs. So width of the clock is the largest skew that you can have plus TW minus TSU plus TD to Q plus TFF plus TSU. So let us just look at all the parameters and then we will go and look at minimums and maximums. So from Cky to Ckj there is TSQ plus TW width minus TSU plus DQ plus TFF plus TSU. So you will see all the parameters appearing here, right. So T clock, the width of the clock pulse, the argument is it should be greater than this expression here with the appropriate maxes and mins. Even let us say there are no maxes and mins, they are all just the same value. So let us go and see why something like this must be true. So we are looking at Di input with respect to Qj, but we cannot do it with respect to just Qj, because it is not just that Qj is changing Di. If the clock is on, if Dj changes, Qj can change, and if Qj changes, Di will again change, right. We want to ensure that there is this chain of events, right, Dj to Qj to Di, we want to control all of that. That is why we have done it in this way. So any change in Dj may actually go back and change Di within the same clock pulse, right. And in fact a change in Di could go through Qi and go back and change Dj also in the worst case, right. So several of these events can happen before the clock this latch closes, right. So what this relationship is capturing is from the opening edge of the latch till the close edge of the latch, what is the relationship. So if there is a change here, this is still in the level of Cky. So, if you look at Ckj, it is still in the level of Ckj. If you look at Q here, that is the delay through the latch of J, and Di is happening here. If Di moves somewhere here, it is possible that Cky is on, and it may actually go and change Di could change Qi. So, this expression takes care of the fact that none of those untoward events happen. We want to keep the data input stable for one full cycle, we do not want intermediate changes. So, this expression T clock tells me that we have to keep, for a latch we have to be more careful, there are a lot more parameters involved, and your T clock should be greater than this expression here. So, I also suggest that just like what we did earlier, you go and argue why the maxes and mins are here, and also convince yourself that this expression is correct. So, this brings me to the end of module 33, and in this module we looked at timing analysis of both latches and flip flops. So, the most important thing for the latches and flip flops is what is the frequency at which you can run, and for flip flops is there a setup violation. Sometimes you are also interested in hold violations. For latches, again setup and hold violations. So, latches are less frequently used than flip flops. So, I suggest that you understand the flip flop material a lot more thoroughly, and once you are more comfortable with flip flops, you can go and look at the material for hold for latches. Latches are used in very specific scenarios, it is not used all the time. So, even if you do not understand latches for now, get a thorough understanding of flip flops, and maybe later when you do a VLSI class or when you go and do your masters, you may have to understand the things behind latches also. So, that brings me to the end of lectures of this week. The thing that is left out is some Verilog lecture for this week. So, we will do that in module 34, and till then bye bye, I will see you in the next module.